Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is fluid velocity and fluid power. Our objective is to examine how a conductor's cross-sectional area and flow rate through it influences fluid velocity, and how pressure and flow rate influence fluid power. Let us begin our discussion with a metaphorical mountain climbing expedition. When attempting to summit this mountain, you may be presented with opportunities for additional exploration, be it some unusually scenic overlook or some radical waterfall just off the path. Though these entertaining diversions do not directly contribute to the larger goal of summiting the mountain, they do contribute to the larger context of the mountain and the journey itself. They are in their own right entertaining. Such is the intention of this lecture. It is to be considered an entertaining side diversion contributing to the larger contextual understanding of hydraulics and not meant to be a tedious bushwhack through thorns. In the interest of expediency, I'm going to kind of blow through the math with the understanding that if you want to bushwhack through these mathematical thorns, this option is available. The larger points of this lecture are quite simple. Flow rate, conductor diameter, and fluid velocity are related quantities, as are pressure, flow rate, and fluid power. Let's begin with a discussion of fluid velocity. Fluid velocity is quite simply the speed of an individual particle of oil through a conduit, be that conduit a pipe, tube, hose, or passage inside a valve or manifold. Individual oil particles can be thought of as tiny, tiny bullets shot down the length of the conductor, each having their own speed, direction, mass, inertia, and level of cohesion to the wall of the conduit and to their neighbors, also traveling with a given velocity. Given ideal conditions, those particles in contact with the interior wall of a straight length of conductor will be subject to more friction and as a result move slower than those in the center. This leads to a velocity profile such that the thin layer of fluid adhering to the stationary surface is creeping along. As we move into the center, velocity increases. This type of smooth layered flow is known as laminar flow. Laminar means sheet-like in that each layer of fluid has its own velocity and they do not interfere with one another. Fluid power systems are ordinarily designed such that conduits are properly sized to accommodate the required flow rate such that flow remains laminar. Beyond a certain fluid velocity transition point, flow becomes turbulent. Turbulent flow is characterized by a chaotic, churning action. Turbulent flow is inefficient and is to be generally avoided. Systems experiencing turbulent flow might run unusually hot and as such exhibit early thermal breakdown of the oil. The velocity at which flow ceases to be laminar and becomes turbulent is yet another exciting diversion called the Reynolds number, which I do not intend to pursue within this lecture. However, suffice it to say that it depends upon the properties of the fluid being utilized, specifically the velocity and kinematic viscosity, a similar sounding term that is a measure of a liquid's resistance to flow. Returning our attention to a laminar flow condition, we can calculate the average velocity of the velocity profile using the simple relationship of velocity equals flow rate over area. Note, velocity is often signified as a small v rather than a large V, which is customarily reserved for signifying volume. To avoid the confusion between these related formulas, I suggest explicitly spelling it out as velocity equals flow rate over area. At first glance, this formula may seem self-evident, but I must caution you that details, notably units, are extremely important considerations. A cursory analysis of this relationship suggests that when flow rate is held constant, and we increase the cross-sectional area, the velocity decreases. This makes perfect sense. Consider a tunnel full of commuters on their way to a subway. Given 100 people per minute entering a super wide tunnel, people in the tunnel can take their time and stroll quite leisurely given the tunnel is wide enough to accommodate this quantity of people per minute. This would be a laminar flow condition with hurried commuters purposely traveling the center relatively unmolested by the slow-moving beggars and buskers lingering by the walls. Similarly, if flow rate is held constant, if we decrease the cross-sectional area, velocity increases. This again makes perfect sense, given the tunnel isn't really wide enough to accommodate this quantity of people per minute. This would be a turbulent flow condition, with every person in the tunnel kicking, clawing, punching, pushing, and crawling over each other's backs to make it to the train on time. Coming at this from the opposite end, a rearrangement of this relationship suggests that flow rate is velocity times area, which again makes perfect sense. When cross-sectional area is held constant and we increase velocity, flow rate increases. Conversely, when cross-sectional area is held constant, if we decrease velocity, flow rate decreases. Sticking with our earlier analogy, given a tunnel filled with Olympic sprinters at full sprint versus the same tunnel filled with slow-moving pedestrians trying to text message each other, we'd expect more sprinters per minute to emerge than slow-moving pedestrians. Let's turn our attention away from the general concept and towards the specific units these quantities are customarily expressed. Flow rate, if you recall, is a measure of volume per unit time, volume itself being a cube of a distance unit. Cross-sectional area is a square of a distance unit. Velocity, therefore, is a measure of distance per unit time. Mathematically, our first relationship suggests that velocity is equal to flow rate divided by area. Distance cubed per unit time divided by distance squared, units of distance squared cancel out, and we're left with a unit of distance per time. Thus far, our relationship seems to be in perfect working order. The problem is that very rarely are compatible units employed for these different quantities. Flow rate is often expressed in units of gallons per minute or liters per minute, and conduit cross-sectional area is often an implied product of a conduit's diameter. Further complicating this dilemma is the fact that fluid velocity may be expressed in units of foot per second, inches per second, meters per second, or some other equally unwieldy choice. This is to suggest that obtaining this scenic diversion, seemingly just off the path, necessitates a little bit of wallowing in the mathematical blackberries. Allow me to demonstrate. Follow along if you wish. Consider a pipe with a half-inch internal diameter carrying 1.2 gallons per minute. We're being asked to calculate the fluid velocity in units of feet per second. Let's start by calculating the cross-sectional area. A conduit with a half-inch diameter has a cross-sectional area of approximately 0.1963 square inches. Now let's perform a necessary unit conversion. A flow rate of 1.2 gallons per minute is 277.2 cubic inches per minute, or approximately 4.62 cubic inches per second. Substituting these values into our fluid velocity formula suggests that fluid velocity is approximately 23.5 inches per second. Performing the necessary unit conversion yields a fluid velocity of approximately 1.96, or roughly 2 feet per second. This is a pretty acceptable velocity figure, and which will most likely result in laminar flow conditions. Depending upon the application, most manufacturers recommend keeping fluid velocity below 15 feet per second between a pump and an actuator, below 4 feet per second in a pump suction line, and below 8 feet per second in a return line. This explains why suction and return lines are often larger in diameter than working lines to keep fluid velocity below these figures. Keeping with this spirit, let's say a manufacturer is specifically requesting a system must keep velocity below, let's say 10 feet per second. However, must accommodate an astronomical flow rate of 64 gallons per minute. See if you can use your understanding to determine the minimum diameter of conduit necessary to meet these requirements. Here's a hint. It's going to be huge, given this astronomically large flow rate. Let's say the following sizes of conduit are commercially available: half-inch, inch, inch and a half, 2 inches, and 3-inch internal diameter. Let's perform some necessary unit conversions. 10 feet per second is 120 inches per second. 64 gallons per minute is 14,784 cubic inches per minute, or approximately 246.4 cubic inches per second. Almost a gallon a second. Like I said, this is a lot of flow. Rearranging our relationship suggests that area is equal to flow rate over velocity. Substituting in the necessary values yields a cross-sectional area of approximately 2.05 square inches. Solving for diameter, or diameter equals the square root of 4a over pi, yields approximately 1.6 inches. Given pipe of this exact diameter is not commercially available, you'd be stuck with buying the next size up. In this case, 2-inch internal diameter does the trick quite nicely. Given the commercially available 2-inch internal diameter pipe is substantially oversized for our required flow rate, we'd expect the fluid velocity to be much less than the permitted maximum of 10 feet per second. Since we've got the numbers right in front of us, our calculations now suggest that the resultant velocity should be around 78.4 inches per second, or approximately 6.5 feet per second. This is most definitely a laminar flow condition, given this manufacturer suggests keeping fluid velocity below 10 feet per second. Realize even in the most ideal of laminar flow conditions, isolated pockets of turbulence will always develop at the inevitable turn, restriction, kink, bend, fitting, or valve passage. Going back to my earlier depiction of flow as individual particles, each having their own velocity, it is for very obvious reasons turns are most efficient when they perform gradual sweeping bends. Any particle with a characteristic inertia negotiating a sharp turn or obstruction would slam into the corner and bounce around the bend, contributing to turbulence and inefficient operation of the system. Often manufacturers specify certain minimum bend radii that a hose must negotiate. For example, consider a hose manufacturer that specifies a hose with a 6 times internal diameter minimum bend radius. This means a hose with a ½ inch internal diameter could at most negotiate a 3-inch radius or a 6-inch diameter circle without being unduly inefficient. We'll examine other conduit characteristics in later lectures.